Okay, I've described here a region E, which is the portion of the sphere of radius 3 above the plane z equals 2. And what I want to do in this video is set up, but not evaluate, an iterated integral in all three coordinate systems to calculate the volume of that shape. Okay. I think this is a great exercise because it allows us to practice setting up the integral, which is often one of the hardest parts. It also is going to allow us to compare them so that we can start getting a sense of when rectangular coordinates are nice, when cylindrical coordinates are nice, and when spherical coordinates are nice. Okay. All right, so if we're working with this region, I'm going to just notice that it's going to look something like this. We've got a portion of a sphere, but it's cut off by this plane at z equals 2. Okay. So I'm going to start finding this in rectangular coordinates. So I know that in rectangular coordinates, I'm just integrating 1. And I'm going to set this up dz first. Okay. I usually try to view things as a simple xy solid so that I'm integrating from bottom to top and then over the projection of that shape onto the xy plane. So I can sort of think of this as the integral over d, where d is going to be the projection onto the plane from bottom to top, dz, and then dA. So let's take a look. Just looking at our picture, I can see that the bottom surface here is that plane, z equals 2, and the top surface is the sphere. Now, if this was the sphere of radius 3, I know that x squared plus y squared plus z squared was equal to 9. So z squared would be 9 minus x squared minus y squared. And then z would be plus or minus, but this is the top part, so this is z equals the positive square root of 9 minus x squared minus y squared. Okay. So I can go ahead and fill in those z limits of integration. Okay. Now I want to work with d, and I want to express this as an iterated integral, so dy dx or dx dy. Okay. So it looks to me like if I project this onto the xy plane, I'm just going to get a disk because I can see that that plane and the sphere intersect in a circle, and that circle becomes the boundary of this disk, which would be the common domain for the floor and the ceiling here. To find the radius of that disk, I want to set my z values equal to each other. So root 9 minus x squared minus y squared would have to equal 2. So squaring both sides, 9 minus x squared minus y squared would equal 4. I'm going to subtract over the 4 and add over the x and y's. So I get 5 equals x squared plus y squared. So my region D, over which I'm integrating in the xy plane, is going to be just a disk of radius root 5. Okay. Now, if I want to view that as a type 1 or type 2 region, I know I want to slice it. I'm going to slice it this way so that the slices would start at negative root 5 and end at positive root 5. So this would be the point negative root 5, 0, and this would be the point positive root 5, 0. So my x values are going to go from negative root 5 to positive root 5, and then my y values will just go from the bottom half of the circle to the top half of the circle. If I solve for y, I'm going to get y is plus or minus root 5 minus x squared. So we'll go from negative root 5 minus x squared to positive root 5 minus x squared. Let's see, these were our z's, these are our y's, and then dx was our last limit of integration. Okay, so there we've got this set up in rectangular coordinates. Probably not what I would choose anytime I'm seeing a sphere. I'm thinking I probably want to use either cylindrical or spherical coordinates. Okay. All right, if I wanted to do this in cylindrical coordinates, what's nice is I've already done an awful lot of the work. If I choose to, in cylindrical coordinates, also integrate with respect to z first, and then integrate over the region in the xy plane, I've already figured out what the bottom and the top are. And I've already figured out what that region is. I just have to describe them differently. So, first of all, I'm going to remind myself that my dv rather becomes r dz dr d theta. I'm still going from bottom to top. 2 is 2. The top surface just becomes 9 minus r squared. And then I was integrating over this disk. Over a disk, my radius would vary from 0, in this case, to root 5, and theta would go from 0 to 2 pi. I'm liking that. That looks like a relatively simple integrand. I didn't make the integral. The integrand isn't super complicated, and none of my limits of integration are super complicated. So definitely I prefer the cylindrical coordinates at this point to the rectangular coordinates. Let's take a look at the spherical. We might think at first glance, because we've got a sphere in here, that spherical is going to be the simplest, but we've also got a plane. And spherical isn't super nice with a plane. Not impossible, but just not quite so nice. So let's take a look. I'm going to draw my constant theta half plane, where here's the z-axis and here's the xy plane. And what I would see in each of those half planes would be something that looked like this. Okay. All right. I know that I'm going to be integrating rho squared sine phi d rho d phi d theta. Okay. I already know the d theta is going to be 0 to 2 pi. That's the same as what it was in my cylindrical coordinates, and we've got the same thing going all the way around. Okay. But what I need to do is figure out my limits of integration for rho and for phi. Okay. So if I take a look at what I have here, I'm just going to draw in some constant phi rays. And I can see that for each of these phi rays, rho varies from the rho value on the plane to the rho value on the sphere. Now, the rho value on the sphere, my upper limit of integration for rho is pretty straightforward. That's just going to be the radius of the sphere. But I'm going to have to figure out here what the rho value on the plane is. And then I'm going to have to figure out phi varies from what to what. So these were just sort of arbitrary phi rays. This one's going to become important. I'm just going to write that's phi equals phi naught. I can see my phi is going to go from 0 to whatever that phi naught value is. But I'm going to have to figure out what that is. Okay. All right. Let's start by trying to find our rho value on the plane. Okay. So for a fixed phi value, I'm basically going to have a picture that looks like this. If this is the z-axis, and this is my phi value, and this is the plane. Now I know that plane was z equals 2, so this vertical distance is 2. I'm viewing phi here as a variable, because I'm trying to express rho in terms of phi. Different values of phi are going to give me different values of rho, because I'm trying to solve for now how far is this distance before I hit the plane. And the bigger I make phi, the longer that distance is going to be before I hit that plane. So I want to see if I can express rho in terms of phi. Well, I've got this lovely right triangle here, and it looks like I've got the adjacent side and the hypotenuse. So I can just say cosine of phi is 2 over rho, which would mean that rho would be 2 over cosine of phi. And it's okay in this case to divide by cosine of phi, because I can see that that's not going to be 0. Cosine of phi would only be 0 if phi was pi over 2. We're not rotating all the way down to pi over 2, because we're not going to hit the xy plane. Okay. So probably simpler to just call this 2 secant of phi. And if I wanted to, I could have gone straight from here to secant. I'm just more used to working with cosine, so I started there. So my rho value is going to be 2 secant phi to 3. Okay. So now I need to figure out what this phi naught is. Okay. I need to figure out what's the biggest phi value I'm going to have before I rotate far enough that I'm going to now intersect the sphere below the plane z equals 2, and that's outside of the region that I want. Okay. So again, I'm going to have a triangle that I can draw. Okay. Now I'm drawing this triangle right here. I still know that this is 2. Now I'm solving for the specific phi naught value that's going to have this be where the sphere intersects with that plane. Well, if this point is on the sphere, then I know that this is a radius of the sphere, so that it's 3. Alternatively, I could use the work that I did previously to say I know that side is root 5, because this is just a radius of that disk that we have where the plane z equals 2 meets that sphere. So I can work with any combination of these sides. I kind of like this one and this one. So I'm just going to say, okay, so cosine of phi naught would equal 2/3. Phi naught would be inverse cosine of 2/3. So my phi values would go from 0 to arc cosine of 2/3. Yeah, I can make that fit. Arc cosine of 2/3, and this was a value of 3. Okay, so even though we had a sphere in here, spherical coordinates weren't super nice. 2 secant phi isn't the world's worst formula for a limit of integration. Arc cosine of 2/3 isn't impossible to work with, but I would say for this particular problem, of the 3 types of systems that we had, it was probably simplest to do this one in cylindrical coordinates.